Yeah, thank you very much. So let me introduce myself. So I'm senior principal architect at Vespa. So I'm currently focused on e-commerce improvements, let's call it like this. So some of you maybe saw this demo. It looks like this demo last year. So that was focused on the sparse tensor personalization, live calculated on the user behaviors. So we did add a lot of improvements here. And one of this is integration of the special visual model, which is extremely efficient in C2C platforms because it actually can embed extremely efficiently lots of embeddings per second, even around 1,000 per consumer-grade GPUs. And also what it does create deterministically located features over the space. So what does it mean? That you'll be able to use that for many things, searching similar products, building a recommendation system, and also use it for arithmetics. I will explain exactly how this works inside Vespa and then how you can do that, but we'll start from demo so you know what is the expected result actually in that. So let me actually first go into, let's say, similar product searches. So all of this, what you see here, it's similar product. So if I search, let's say, gold heels, then we have gold heels. Now we look for the similar products. You see that the color, shape, and everything is very similar, right? So searching with this model and Vespa itself combined, for example, we'll use t-shirt with Mickey Mouse. So now we can actually find t-shirt with Mickey Mouse, right? So now we created something which enables us to modify these tensors on the fly. So what does it mean? That we go into the, let's say, new view where you have similar products as you see here. This is our anchor element. Anchor means that we have the embedding from that item here. But then I can dynamically create now my own filtering or adjustment rules. So I would say Mickey Mouse. And then I'll add, so what happened here? I got the tensor created for Mickey Mouse, right? So I have now two tensors. Tensor is equal to vector, basically. Vector is tensor, so you can exchange it in this space. Vector is just flat one dimension. Tensor is vector. So now what I will do, I will minimize input to that. So you'll see in the presentation how this is calculated, and I will remove Mickey Mouse from the picture. So now I remove Mickey Mouse only, the rest of the parameters are preserved because, as I said, model is deterministic. In Vespa ranking, we can use directly the operation arithmetics. So then effectively we have these results. But then I will show you something more. Earrings, I specifically make mistake in this. Earrings with blue stone. So now we have earrings with blue stone. So I will start with the model itself, how nicely it enables you to navigate through the pictures. You see that basically the shape, the colors, everything is preserved. And then basically here in this data set, I have 1.2 million items. So those are spread around all the, let's say, clothes, items, basically apparel, all the apparel. So it's not that easy to find very similar products with the embedding model like this. But then we enable that here. So now let's imagine we like this kind of earrings, but we don't like blue stones, right? So we'll do blue stone. And then we basically add red stone. So I will minimize blue stone, increase red stone. And now I will do the search. So what you see here, the shapes, styles preserved, but then one element, which is stone, is modified. So what it gives you actually here, this kind of operations, it gives you chance to update the tensors on the fly with other tensors. Actually here, I have not single tensor, as you see, a single vector. I have two of them. So what we do, we formulate matrix out of these vectors. Matrix is multi-layer vectors. We have another vector which is actually scoring. So these sliders provide the scoring. And we multiply, we collapse, normalize, and we then add and operate on the fly with this. So that's one part of the demo, so you know a little bit how this is actually giving us the perspective. Then the other comment, I didn't include that in our demo here, the facets, because the core concept of this is that it enables you to create the faceting out of the vector embeddings. So probably no one from you actually yet think about creating embeddings from vectors, but how we can implement this. When we have this type of embedding, and then we have Vespa, we can now embed every element like this. Then we can embed the phrases, or let's say, I will call phrases which were used for the training of this model as we expose them. Actually, we have them because we trained the model. Actually, our partner trained the model. So we know what were the phrases and how they've been matching the visual clues from the images or apparel, right? So now we embed all those phrases into the same, let's say, vector space as images. Now we can use this tensor to search against these expressions. So now we have list of scored, let's say, facets. Now we can put that facets into something like you see here, and users can decide what they like more, what they like less, and they can scroll. So then this doesn't need to be dynamically created by users. It can be auto-generated by what image is presenting. And obviously, if you'd like to add something more from your perspective, you can guide your user on your website. Maybe you'd like to add color. So you can put color green, for example, and then swipe green more. And then the products will change. So this can be tested if you come to my booth. I will not show you a lot more here because we need to go actually through the slides as well. But if you come to our booth, I can explain more details how this is working and then what else. You can test even queries if you want to this model, and then how you can modify these things here. So now let's switch to the other demo. So I was thinking that to show the Vespa powers in dynamic ranking is also to talk a little bit about tensors, which are actually scalars. A very trivial thing, right? Tensor is scalar, tensor is vector, tensor is matrix. We didn't talk about the easiest one. So we thought that, okay, so Vespa provides something more than typical search engine because we have this ranking which enables you to capture all the signals from all the environment, from the documents, from temperature, weather conditions, user interactions, whatever that is, right? So you see here, I'm not sure if this is very visible. So you have popularity rate, we have clicks, we have reviews, we have temperature, and then we have rainfall, right? So those are different distinct signals. The weather conditions, this is something which you can ingest from the weather forecast, for example. But then all these, let's say, parameters here related to the user interaction, those can be actually stored in the feature store, in the items, whatever else, but they are updated based on the user interactions. And why we actually believe this is extremely good use case for Vespa is because Vespa enables you to do partial updates. Partial updates is the type of the update in the dataset where you update only one field and also can be updating only one cell in vector. Not a whole document like in other solutions, but one field, one tensor, and tensor field. So by these updates, obviously, we can control all the metrics, click-through ratios, conversion rates, directly in the items very efficiently. So now let's see what happens when we modify the temperature. So you see the clothes are changing, and then actually offer changes with the temperature. So we go to the summertime, hot, we have now this. But let's see what happens when we include slightly, now we have this kind of elements, right? But you don't see a lot of rain-focused things, right? But then we increase this slider with rain more, and then what we see? Light, summertime, clothes for rain. But then if we move it to wintertime, look what we have. So it's changing dynamically into this space. But now within this space, if we actually move with popularity, you see that our documents are changing, but they are still staying in the same winter clothes, right? If we move it here, still staying. If I move here, then we can apply business logic nicely within the area of interest, or let's say space, which we do. So what we can enable everyone who will be willing to, let's say, play with Vespa, that you can apply all the business logic, all the fancy ranking, and then, let's say, modifications, detections, and stuff like that, really real time in the system. So let me actually now start with the presentation. So maybe one quick announcement, if you'd like to learn really a lot from the people who are using us, we have conference in September, Vespa Live. So top people from biggest shopping industry will be here. So now we'll talk about this tensor operations in ranking. So maybe I'll ask you, how many of you are very familiar with this, tensors? Maybe you raise the hands. Okay, so this is perfect audience then. So, but then just to repeat for those who didn't think about that a lot. So everything basically which we use in mathematics is tensor. So number is a scalar, is a tensor, but then simple one single number. Vector is basically one-dimensional representation. But then tensors can be sparse and dense. Sparse means that you have key value pairs. So let's say you have weight, and then you have value. Dense is basically just the value, right? And then we have matrix. We showed this tree to actually comprehend this easily, but Vespa enables you to do even more complex dimensions. So you can do even three-dimensional objects and more. And why this is so important that we are able to represent this, and then we can also do all the primitive tensor operations in Vespa. So those reduce, join, map, concatenation, those are the primitive functions to create any other higher level functions, which is basically, as you see here.
I was a bit confused because I'm hearing the speaker at the same time.
Yes. Here we have cosine similarity. We'll see later on how this is calculated with the tensor operations. So all of this and many, many more actually functions, even ReLU activation function, sigmoid, when you build neural networks, this is the tensor operation. So the tensor arithmetics, which you'll actually see in the demo, this is the simple operations. So multiplying, dividing, adding, subtracting on the tensors, right? So this is very simple topic, mathematical. And now why tensors are very good for personalization. So how the personalization is working. So when you have items, so two-tower recommendation system, for example. Right?
I hear you, but I cannot understand because
representation, vector representation from the item, from the user. Sorry. And now you either use models to generate user space, or you update directly from the item to the user with decay functions. So you basically remove a little bit of the weight from the user, then you combine that with the item, and then every time user interacts with the item, you will shift and modify user vector to reflect more interactions with the items, right? So this will be adjusting to his preferences, to his color shapes and everything.
Okay, now
So effectively, by doing this kind of mathematics operation, adding these tensors and reducing the values, we'll be having really nice personalized experience. And this is purely in the vector space. So now the next thing is control vectors. Control vectors are these vectors which will modify the meaning. So as you saw when I was changing the color of the earrings from blue to red, this is actually the control vectors. So this is actually coming after discussions with my colleague from the Vectra model. So he created this model, and then he created these concepts that we can have deterministic spaces, and we can operate like this with the control vectors. So obviously control vectors based search. Now what you'll get actually from the for the users, that user can actually have something more leather, or something more green, or more formal or less formal, because model recognize formal and not formal, for example, dresses, right? So you'll be able to shift the same colors, maybe the same flowers on the dress, but the one will be formal, the other one will be very summer for the beach only. And you can do this kind of experimentation with this kind of solution. So we have this anchor, let's say product or item detected, so first embedding. Then you have steering representation, so natural language expressed facet, as we said, or facet, or the steering source for the tensor generation, the same space as the document. And then we blend that, but we'll need to weight normalize. So we do L2 normalization when we actually collapse the vectors together, so not to grow too much in particular space, because if we don't do normalization, then maybe color will become too strong, or maybe some shape will become too strong, so then it will be matching wrongly. So we do this normalization. So effectively, from the user perspective, you can actually see this will be heavy value, because no platform at the moment on the market allows, when you have big data set to find really the things you like. Or maybe if you see something, but you like that with the flowers, it's impossible, right? So with this solution, you can actually really provide something outstanding from the market itself. So how this is working in Vespa itself? So we have query parameters, as you see here. So we have original vector tensor, then we have feature matrix. So this is what we define from the text itself, and embedded, so that becomes matrix. That's why we have this representation, as you see here, features, and then vector. So this is basically multi-dimensional.
Everything is fine, right?
And then we have
I just need
weights.
to have my
Weights is slider values.
Okay.
And then we effectively weight feature, so reduce a matrix and weights. So basically then we created weighted tensor. We blend, so we basically multiply, update, normalize, and we create dot product. So in Vespa operations, I'm not sure if this is very visible, but then you see how this is represented in Vespa. So this is very simple expression. So if you imagine how you would do this kind of thing in other system, it would be not 3 expressions like this. So in our ranking profile, you just put this, and it works as you saw. This will be the result. So very fast, and then also scalable for the production traffic, because obviously those are very simple tensor operations for Vespa. They are executed on SIMD level operations in CPU. So this is really accelerated, and it will give you the fast results. So I think probably this is very not well visible. I'm not sure if I can make it bigger, but I will just explain. So you have here expression dot product is reduce and multiplication of 2 vectors. Vector norms is a square root from power of 2 of the tensor. So this is so this is vector norms. Cosine similarity is dot product divided by the multiplied norms from the 2 vectors here. So this is, as you see, function which which you can develop. Even cosine similarity, I don't think in other systems you will be doing primitives like here, but then you have really high possibility to customize anything from mathematics perspective. Then in Vespa also you can do fallback functions, graceful fallback. So in my case, when you notice that when I didn't provide any tensors, obviously I expected in my ranking profile some inputs. So this will be filled with zeros, not present. But since we have if conditions here, so if it has features, and features actually is calculated by reduce features vectors multiplied by each other and then bigger than 0. So this will be true or false, and then if true, then I have multiplied by vectors. If not, I fall back to the original vector. So you see properly presented result based on similarity of existing document, not the document which is multiplied by zeros, which will be actually not good, right? So you have conditionals in Vespa ranking profile, so you can do multiple different decisions as well based on different conditions. So you can use even different embedding models if you want based on conditions or finding different, let's say, weights or values. And why this is really cool from my perspective? Because then you can manipulate with everything on the fly. So it can be related to your user, temperature, items, anything you want. So you can do close modal steering. So you don't need to work with image to image, like image search. You can work with image and text and blend them together, right? So this is something which I don't think in many solutions were visible. So you can do positive and negative. So you can remove, like you saw my Mickey Mouse operations, I removed Mickey Mouse, I removed blue, I added red. But obviously much more complex and many more things can be done. So you don't need to reindex embeddings. You don't need to do some special models tweaking, but you just modify them on the fly in ranking at the commercial grade scale. And then obviously you can control what's missing. Robust degradation means that you can control with if conditions, basically this kind of easy syntax. What you like to avoid, you can create edge cases, handling, and so on and so on. So, which is really useful. So I think you listened a lot about this. It probably requires more time to actually think about this, but those will be the key takeaways, that you can use these vector models, which is something which I'm thinking is not very visible on the market at the moment. That is super small embedding, 256 dimensions, very fast to infer. It was very expensive to do this kind of operations in the past. Now with this model you can do it fast. then we can do that in the real time or the query time evaluation of this, modifying and do everything. We can do cross-modal operations, and then we can do personalization as well in that. So thank you very much. And once again, maybe I'll repeat that the day after tomorrow, we have Future of Search, where we'll do workshops and we'll show how this can be done in Vespa. So if you'd like to visit, you'd like to play with this, then we'll put a lot of more time to explain all the details on Thursday during the day. Thank you very much, and maybe there are some questions. I don't know, do we have any time left?
Thank you. Thank you very much, Piotr. Unfortunately, we don't have a lot of time for questions, but I'm sure a lot of people will stop by your booth, Vespa. So Vespa is present for all the conference here at the booth. And just a small announcement, because I'm in charge of selling fashion outfit also. So if you want, you can stop by the registration desk and get your Berlin Buzzword t-shirt. So this year, the color feature has been switched to the green color. But
Thank you very much.
Thank you.
Thank you. Bye.